Hello and welcome to Fullerton College's pre-press class. This is Professor Ben Hewitt. Today we're going to look at the PIA's pre-press training manual, task 4, module 1, color theory. We are now entering the part of the course in the curriculum that this instructor really enjoys. I really do love color theory and how it works, and parts of it are scientific, parts of it are psychological, parts of it are entirely subjective. And it's very interesting to put all these things together to try and define something that we all experience together, but no one can exactly put their finger on. The idea of color. We're going to look at how image capture works and how that is a part of the imaging process. How do we capture images? How do digital cameras and recording devices, how do they sense the world, and what is it that they are doing that makes the images that we see on computers? We're going to talk about the electromagnetic spectrum and how light is just a part of it, and how it is a form of wave energy and sometimes acts like a particle. We're not really going to talk about the particle wave duality very much in this class because that does not affect color perception that much as we understand it to anyways. We're going to look at additive and subtractive color models, how they mix together to make what we see, and to some extent, why they work, and then also why they don't. They are models, and models aren't exactly the truth. Um, they need only be able to show that it works. A model is not necessarily an explanation. If you think about some of the older versions of the solar system involving circles within circles and gears and clockwork all working together to make the planets orbit the way they do around the sun or even around the earth, some of them may not be accurate physically to how the actual solar system works, but they're still accurate and predict the planets in the right places and the right times and the right seasons. So a model can show you how things are, even if it doesn't show you under the hood of exactly why it works. Sorry for the side note there. So let's talk about definitions here. Remember that a printing class in a lot of ways is a language class. So when we're talking about color, color is known as a phenomenon of light. It's a visual sensation. And phenomenons are things you understand through your senses, not through thought or intuition. You cannot, well, I mean, if you know enough of it, you can, but we don't deduce color. We don't sit there saying, my dear Watson, I do believe that's going to be red. Not exactly. We don't deduce it from evidence. We experience the color red when we see something that reflects the right. I shouldn't even say that. Let's go even more basic. We see something as red when the correct wavelengths of light reach our eyes, and our eyes tell us, hey, that color is red. And the experience that we have with the color and what we see in our own visual systems in our each individual human bodies that we live in, those are more like tastes or smells than they are like math or a scientific fact that we can memorize and understand. There are things that we experience. The best way to think about it, and especially if we need to explain it to a client, is to think about it in terms of color versus taste. Because how can you be sure that someone else is experiencing the same flavor the same way you are as you both eat the same slices of the same pizza? Some people like pineapple, some people don't on their pizzas. Some people think it's a crime against culinary arts. Some people think it's the best thing ever. I don't want to lose any students, so I'm not going to tell you which side of that argument I'm on, because either way, someone will be mad at me, and it's not worth it for that. But the point is, flavors act differently to different people. Some people think that certain things are delicious. Some people think they are utterly disgusting. Anyways, the whole point is everyone experiences it differently, even if they're all eating out of the same bucket of chicken, so to speak. Everyone's going to be experiencing those herbs and spices a little bit differently than each other. We are in no way sponsored by any chicken restaurants. Sorry for that analogy. But if anybody wants to sponsor me, I'm open to it, especially if it comes with free chicken. Anyway, so also a theory. We're talking about color theory. A theory is a scientifically acceptable general principle that explains a phenomenon. Because a phenomenon is something that we experience. We have scientific theories to explain, why are we experiencing this? What is it that makes us see this, smell this, hear this, taste this, feel this? And it's also a bit unproven. Some of them are very hard to prove. You can't exactly prove someone else's experience. Not exactly. There are steps being taken and have been taken to try and, you know, tame the Wild West, so to speak, of color and how it is this just frontier of knowledge and experience. It's not fully defined. Maybe that's what I find so interesting about it. So, the physical origins of color. As far as we experience color, we experience it because of how our eyeballs are built. Our eyeballs have two types of nerve ending in the retinas, in the back of our eyes, that let us see different things. Most of our eyes are covered in something called rods. They call it this because they are actually shaped more like rods. It's actually the physical shape of the sensor in our eyeballs. And these rods, we have determined, can sense differences in light between bright and dim, light and dark. Our primary mode of seeing, although we see all sorts of colors in our world, our primary mode of seeing is black and white. We only see light versus dark. In fact, if you ever go outside at night, we actually have pretty good natural night vision. Maybe not as good as a cat's, but it's pretty darn good. And we can see things at night with very little moon or starlight. I've actually used to do a lot of night hiking trips when I was younger and didn't have kids. And my friends and I would go backpacking in the desert. And we wouldn't even use flashlights. If you're not under tree cover, you can actually see for miles just using starlight. And it's a really interesting, mysterious feeling to be out there and seeing no color at all, but still seeing the landscape for miles and miles and miles, bathed in a silvery light. And we didn't even need to use flashlights. Unless we were like trying to read something or get into backpacks and look for stuff. Anyways, the point is, we have really good night vision, but it's all black and white. You need to see more, there needs to be more color available, more color, I'm sorry, bad llama. We need to see more light. There needs to be a greater intensity of light for us to be able to activate our cones. The cones are, oddly enough, cone-shaped nerve endings in our eyes, and the cones are receptive to wavelengths of light. They tell us not only how much light are we seeing, but what kind of light are we seeing? Should also mention that the human vision system is not just the nerve endings in your eyeballs. The human vision system also involves your brain. The vision system is not only what signals come in, but how are they interpreted? And it's something interesting to watch happen, as I can say, as a parent when you have small kids. Babies are just learning to use their eyes, and they haven't yet corrected for things yet that we correct for all the time. They haven't yet tamed their vision system into an understandable input source. So to them, it's just all sorts of wild, chaotic light. And they slowly understand what faces look like, and they slowly understand which way up is. And things appear upside down for a while. Anyways, the point there is, we have a vision system that consists of our eyes and our brains interpret the signals the eyes are sending them. Anyways, one of the things that we're extremely good at is comparing color. We put two things next to each other and we say, are they the same? Yes or no? How close are they? What is it similar to? What is it different from? We look for, just like your elementary school writing and your high school, middle school, and high school writings, compare and contrast the blah, blah, blah to the blah, blah, blah. It's always compare and contrast. Well, guess what? That is one of the functions that the human brain is very best at. We are extremely effective comparison judgment machines. Maybe it explains some of the problems we have in society just a little bit. If that person over there doesn't look like the people you're used to seeing, well, then they're different and therefore wrong. I know everybody has some twinge of that built into them somewhere, and sorry for whatever parts I have. I try not to have them. But anyways, the whole point is we see things on their own. If you see only one thing by itself, trying to determine what it is not the same as putting two things next to each other and saying, how are they? We do see color difference as well, especially among lighter colors. That has to do with the fact that the more that the rods in our eyes that see light to dark contrast don't need very much light to be sensitive. But it takes a significant amount of light to be able to use our cones. You need daylight more or less. And even then, the brighter the daylight is, the more things you're able to see. So lighter colors, brighter colors are easier for us to differentiate between rather than darker colors. Let's talk about chromatic adaptation. This is actually the brain version of what a lot of common digital cameras will do for you, which is called white balance. If you've ever looked at your digital cameras and the settings on there, there's always a white balance setting, which you can use to adjust. And basically it does this, it was designed to do the same things that your eyes do. And I don't just mean your eyes. Understand when I say eyes, I mean your vision system. You as a person, as a human, when you see things, your brain is interpreting the signals. And one of the ways that it does it is called chromatic adaptation. It adjusts to overall color shifts so that things look normal to you, depending on what kind of light you're in. Let's look at a demonstration here, and then I'll talk about it a little bit more. So as the slide says, folks, take a look at the woman reading the newspaper with the man there. She's wearing a yellow shirt, right? I know I'm leading the witness here by saying that it's yellow, but it's mostly a yellowish color on that shirt. But if we put a blue, or like we'll call it, I'm calling it blue, but a cyan filter on top, you'd probably expect it to look different. If you add blue over yellow, what do you get? Yep. If you cover just her shirt with a cyan filter, her shirt starts to look green. But check this out. If instead of just her shirt, what if you do blue or cyan over the entire image? Looks yellow again, doesn't it? That is because of chromatic adaptation. Your eyes will adjust for whatever their surrounding color is. So if you're in a room that has like a red lighting, your eyes will adjust for what colors should look like. Some of it's based off of memory, some of it's based off of, that's right, comparing colors to each other. Now, in this case, I have to switch to another sentence for my analogies because overall, it's good to describe colors as being like flavors, but what if it's like music as well? Because this is where it works. I don't know how many of you have done much or know much with music. A lot of people enjoy it, whether or not they play it or study it. I myself was a band nerd for a while and a pretty decently accomplished trombonist back when I was in school. So anyways, bass clef guys, all the way. Also spitting into brass tubes. That's what I think fun is. But the point here is, if you understand a little bit about music, you might understand about the keys, the key signatures. Depending on how high or low your instrument or voice can play or sing, you will want to play a different scale of notes. They all sound the same kind of thing. I mean, I can put the song up for you if you need some Sound of Music out here, because Julie Andrews is a treasure. But the whole do, re, mi, fa, sol, la, ti, do, you can do that and be correct or wrong with it, so long as the interval spacings, and I apologize, I'm really not a singer. I told you, if I'm doing music, it's spitting into plumbing. That's how I play music. I don't really sing. But anyways, you the notes you sing, the scales that you play, the basic octave, at least in Western music. There are some very interesting differences in other musical traditions that I'm super interested in, but don't have any bearing on my color analogy. So some other time off the record, we can talk a little bit about Japanese music tradition, which is super interesting and really cool sounding, especially to Western ears, to which it sounds familiar yet hauntingly different. But anyways, the point is you can play different, as long as the intervals between the notes are the correct intervals in the pitch of the song, it sounds correct, even if it starts on the wrong note. You can sometimes, some songs that want to repeat a lot, especially sometimes with religious music where they really want a song to go longer, but it's not that long a song, they'll take a key change where they will suddenly go up a step and sing the same song a little bit higher. And professional musicians do this in normal music as well. And it's a thing where it still sounds like the right song to you, even though it started on a different note. That's because the relationship between the notes is what makes the song sound like a song, not any note in its own. I mean, you can have perfect pitch. You can sing a concert C, and it'll be exactly the same as a well-tuned piano and the agreed upon tonal qualities of what that note should be. Or you can sing a C that's totally off key, but as long as your other notes are the correct relationship to that first note, the song sounds like that song. I've gone way too long in this analogy. The same thing works for your eyes. Your eyes will look for the brightest part of an image. And that could be an image that's printed on a computer screen or in person. It'll look for the brightest light it sees, and your eye will say, well, if that's the brightest thing in the room, so to speak, if it's the brightest thing, that must be white. Therefore, I will adjust everything you're thinking you're seeing so that you see you count that as white and you understand all the other colors in relationship to that as white. I'm about out of time for this first video. Sorry, I'm yakking on and on about this, but again, I really enjoy this stuff. It's super fascinating, isn't it?